Okay, let's get started. Is this working? Can people hear me? Okay, let's get started. Any volunteers to say a prayer? Thank you.
Father, we thank you for the opportunity that we have to meet here for class. Thank you that we can in person. Please help us to continue to learn and grow and to keep our eyes open for those who need help. And say things in the name of Jesus Christ. Amen.
Amen. Thank you very much. A few things before we get started. We have a test coming up the 25th through the 29th, so near the end of March, a few weeks away. So it's not immediate, but it's coming. So there is a Lynn Robbins, member of the presidency of the 70, gave a talk a few conferences ago about repentance. And in there, he talked about one of his physics professors here at BYU, and the physics professor, he said, would allow you to take exams as many times as you wanted. And he talked about how, that was a good policy. I don't have that policy. It's actually just really hard and time consuming to write exams. I mean, I wouldn't mind doing it, but I do have a repentance policy. I will replace your lowest midterm score with your final score if the final is higher. Okay, so there's opportunities there if you didn't feel like you did really well on your midterm, or especially if you did really bad, you're like, oh no, I'm not even gonna pass or whatever. Nope, you still have lots of chances to, or you still have a chance to bury that score and get better. Of course, you have to do better on the second exam than the first exam, and then you have to do better on the midterm than the first exam to have that work. But if you do really bad on the second exam, then your final can replace that score. So for those of you that didn't have midterm scores, I apologize because we had those 10 or so tests that kind of got lost. We found them and they're up. So okay, any questions before we begin? We're going to go over a few things, and then kind of in the middle of class, we'll have another opportunity to ask questions about the basics of this section. So, so let's go ahead and I'm going to give you some time to work on these problems, and then we'll make sure you understand them. We'll go through them, and then we're going to dive deeper, and we'll talk about one application of eigenvalues and eigenvectors, and we'll talk about kind of just some high-level stuff. So, and Michelle's writing the homework up on the board over there. The determinants is the next section. We're going to take 2 days to cover determinants. So there's a lot there to cover. So go ahead and work with the neighbor on these problems. If you have questions, just raise your hand or talk to your neighbor. They can probably explain it better than me. Okay, take about 1 more minute, then we'll start talking about these. All right, so let's start with number 1. So the question is, are either of those an eigenvector? I guess if you're a pirate, it's an eigenvector. 2, 3, or 1, 1. So if you're just checking, then you can just check the multiplications. So you can take the matrix times the vector. We're doing right multiplication. So the matrix times the vector, we get 7, 7. Is 7, 7 a scaled version of 2, 3? Is this the same? Can I get 7, 7 just by multiplying this by a scalar? No, I can't. There's no number I can just multiply by to get 7, 7. So the 2, 3 is not an eigenvector. So, but if I multiply 1, 1 by this matrix, I get 3, 3. And that's the same as just multiplying it by 3. 3 times 1, 1. So since this matrix, so here's the key, the matrix times the vector is the same as a scalar times the vector, then this vector is an eigenvector. So it's the same, multiplying by the matrix times that vector was the same as multiplying by a non-zero vector. So it scaled it by 3. So my eigenvalue is 3. For that particular vector. So that's the question number 2 asked. 3 is the eigenvalue. So what is the eigenvalue associated with the eigenvector up here? Okay, and it's 3. So questions about 1 or 2? Okay. So number 3, 3 is the big one. So this is like a process you're going to do a lot throughout the rest of the semester. We'll look at determinants for 4.2, but 4.3 is looking at eigenvalues again for things larger than 2 by 2. So eigenvalues and eigenvectors. So we're going to be doing 3 by 3s and 4 by 4s. So this process here is a big one. Like this will be on the next exam. It'll probably be a 3 by 3, but the process is the same. Okay. So how do you find the eigenvalues and eigenvectors? First, you try to find the eigenvalues. And the way you find the eigenvalues is you subtract lambda off the diagonal. We use this. This is the key thing right here. Okay? Because you should be clear on where this comes from. So if we want ax equals lambda x, lambda is the Greek letter L, like makes the L sound from what I understand in Greek. So if we want to find, if we want this to be true, you can subtract lambda x from both sides. You get 0. This is a 0 vector. And then you can factor out the x, so you get a minus lambda I. We're going to think about this as a matrix now, because a matrix minus a constant doesn't make any sense. Right? It's not defined. So equals the 0 vector. So we're thinking about the A matrix minus lambda times the identity matrix with however many things we have. We're just dealing with a 2 by 2, but there's the A matrix minus lambda. This becomes lambda down the diagonal. Okay. So you get A minus lambda. So you're going to end up subtracting lambdas off the diagonal. Okay. Hopefully you got that was clear from pre-class instruction. And this needs to be non-invertible. So the determinant, we want this so the determinant is 0, because that's one of the equivalent statements to being non-invertible is the determinant is 0. So we know how to take the determinant of a 2 by 2, multiply this diagonal, you subtract off the upward diagonal, factored it here, and so you set it equal to 0 and solve. Okay, and so we get lambda equals 1 and lambda equals 3. So these are the eigenvalues. Eigenvalues of of 2, 1, 1, 2. Okay, but each of these will have a vector, maybe more than one when we get into larger. Well, in this case, they just have one, but each of these will have at least one eigenvector. How do we find the eigenvector associated with that eigenvalue? Well, we go back to this guy right here, or this guy, where we're going to have a matrix and we're going to subtract off these values to get new, 2 new matrices, okay? And the eigenvectors are the null spaces of those 2 matrices, okay? Or the eigenvectors are a basis vector for the null space. So if you subtract off, if you put 1 in here for lambda, then you just get 1, 1, 1, 1. So you get this, and you row reduce. You've got a free variable. You better get a free variable, otherwise you found a wrong lambda. But and then you solve for the basis vector, which in this case is a -1, 1. So lambda equals 1 is an eigenvalue for this eigenvector. So they come in, they get matched up. So 1 is an eigenvalue for this eigenvector. So they're kind of in pairs, although you might have an eigenvalue it's associated with more than one eigenvector. And then the same thing over here, if you subtract off 3 from the diagonals, then you get -1, 1, 1, a -1, and then you row reduce, you get that x1 minus x2 has to equal 0, so x1 has to equal x2, and x2 equals x2, so a basis vector is 1, 1. So this is another eigenvector, and that's the one associated with lambda equals 3. So those go together. Okay, questions about this process of finding the eigenvalues and finding the eigenvectors? Yes? Okay, yeah, great question. So it was, why does this matrix have to be non-invertible? Why do we care about it being non-invertible? It comes back to this algebra. And so once we get here, once we get here, what we have is a matrix times a vector that equals the 0 vector. But we're going to specify that this is a non-zero vector. So we only care about non-zero vectors here. So if I have a matrix that I multiply by a non-zero vector to get a 0 vector, then that has to be a non-invertible matrix, right? Because if we know an invertible matrix, the only solution to the homogeneous system, if you have an invertible matrix, is that X is the 0 vector. So that's the big key right here. Great question. So I know this has to be non-invertible, and then I use the fact that the determinant of a non-invertible matrix is 0. So I try to find the values of lambda that make that determinant 0. Nice. Yes?
Does it work to subtract off the other side? So instead of having a minus lambda I, it's actually I lambda minus a?
The question is, does it work to subtract the other way? So have lambda I minus a. Right, can you find the determinant of lambda I minus a? Or later here, like, can I do lambda minus 2 minus 1 minus 1 lambda minus 2? So that would be that matrix in our case. Yes, you can do that. That works just fine. Yeah, because over here, if you subtract the A over, you can do the math. So, yep, should be just fine. You do end up having to change lots of signs this way, but I know it's nice, especially when you get to a 3x3, you end up with a negative lambda cubed, and most of you will like a positive lambda cubed. So even if you don't do it, most of you will multiply by a -1 once you get the equation to make that lambda cubed positive. So, but yes, you can do that. Nice question. Okay, other questions? Yes.
Is there, so in the case we've been working with, we've had like 2 eigenvalues, I think. Are there matrices where you never have eigenvalues, or you only have 1, or like you have up to like a huge amount of number, a huge number?
Great question. So that question was about the number of matrices. Are there matrices that don't have any? Are there matrices that might have tons, or just one? There's always at least one. Okay. It might not be a real number, so it could be complex. Okay. Rotation matrices. Well, we'll get to rotation matrices in a minute, but yeah, they don't always have real eigenvalues, and the eigenvectors might not be real eigenvectors, but they have them. There will be matrices where 0 is an eigenvector, and they might have you might just have one eigenvalue, and it's associated with a bunch of eigenvectors. That's also fine. So, yeah, we'll explore more of that in 4.3. But yeah, it's not always two, like in this 1301 or maybe something like this. This only has one eigenvalue, and it's 1. And I think there's 2 eigenvectors here, but yeah. Yes?
So in the case of a complex eigenvalue, I just watched a 3 Blue and Brown video like an hour ago.
Oh.
And he said that it corresponded to a 90-degree rotation.
Yeah, so that question was, the student just watched 3 Brown, 1 Blue, and he talked about how an eigenvalue of a matrix that is I, like the complex number I, corresponds to a rotation of 90 degrees. Yes. And if it's not just I, but some complex number with, then yeah, there's some rotation thing going on. And because if we rotate the plane, if I rotate the plane any amount, and stretch it, I can stretch it if I want to, but if I rotate any amount, I can't have an eigenvalue. I can't have because an eigenvector is one that stays on its span after I do the transformation. But if this is, and so yeah, if this is a vector, represents any vector, and I twist it, then and maybe stretch, this is going to be the new one. And like no eigenvector stays on, no vector stays on its span when you rotate. Oh, so the like the z vector here?
Yeah, like is that kind of
yeah, so if you're in R3 and you spin it that way, then yeah, that's kind of what's happening. But if you're only in R2 and this is the point and you're spinning it, there's no vectors in R2 that stay on their span. So yeah. You might think that I wish we had more time to talk about complex values and modeling with complex values, because I know most math students think, hey, they're imaginary numbers that are useless. It turns out that anytime you have cycling phenomena, you end up with imaginary numbers in there. Engineers will work with them all the time because, or yeah, things that rotate and things that cycle and go back and forth, they end up with complex. You end up with complex numbers in there to model the phenomena. So, but if you don't like complex numbers, you can actually, there's a matrix you can just use instead of I. So there's a 2x2 matrix. And then you can just use that and you don't ever have to use I. But we don't have time to to delve into that, but I wish we did. Okay, other questions? Okay, let's do, this is just a practice thinking conceptually about eigenvalues, kind of about this idea. I already did talk about the rotation, but just think about, you're not trying to solve here, just think about what are the vectors that stay on their span. So you can start with a vector, oops. Start with a vector, and you can think about the line that it's on, and then after you do that transformation, does it stay on that? Does it stay on there, whether it's this way or this way, I mean, whatever vector it's on. That's one way to think graphically about to help you find eigenvectors. Okay, so if you reflect across the line y equals x, can you think about what there are two eigenvectors there? Can you think about what they are? If you double the y component and triple the x component, can you think about find vectors that stay on their span? So take a few minutes and think about that. You can talk to your neighbors. All right. Okay, I already gave some of this away from earlier, but let's go over this. So here's the line y equals x. Okay, how many eigenvectors are there with the transformation reflecting over the line y equals x? I heard one. I see 2 fingers. Okay, there's 2. You can only have, if you're working in R2, if you're working with a 2 by 2 matrix, you can only have up to 2 eigenvectors. If you're working with a 3 by 3, you can only have up to 3 eigenvectors. Okay, so usually there's 2, but there you could have 1 or you could have 0 real ones anyway. So what is one of these? Someone raise your hand. Tell me where one of these is. You're raising a finger.
Yeah, I was just thinking, I think I could. So one would be
Perpendicular to the axis of reflection. So like this one. Yeah, perfect. Well, you'd pick it pointing the other way. Doesn't matter. So that's the answer to number 4. I forgot to talk about number 4 on those first problems. It said, what if you double an eigenvector? Is it still an eigenvector? Or triple an eigenvector, or k times the eigenvector? Yes, you can scale an eigenvector. It's still an eigenvector. And yeah, that's the big point there. If you scale an eigenvector, it's still an eigenvector. So there's not just one eigenvector pointing this direction. Anything on this line, any vector on this line that's non-zero would be an eigenvector. Okay, what would the eigenvalue be associated with this eigenvector? So the eigenvector itself, the eigenvector would be a -1, 1. Or we could do, sorry, 1 a -1. So that's an eigenvector. Or we could do a -1, 1, either way. But what's the eigenvalue? If I do the transformation, that should be the same as multiplying that by a scalar. So the question is, what's that scalar? -1. So the eigenvector, this is an eigenvector. The associated eigenvalue is -1. Okay, so someone raise your hand.
I don't have the next one, but why is it -1? Won't that change it from 1, -1 to -1, 1?
Yep. So the question is, why is it -1? It won't it change it? It will, but it changed it. It just scaled it, right? This is just a -1 times that. So it's still on the span of this line because I reflect that. Now it's just pointing this way, right? So doing that transformation, we could write down the matrix that does the transformation. Multiplying that matrix times this is the same as multiplying it by a -1. So since it's the same as multiplying by a scalar, then that scalar is the eigenvalue. Nope. There's only one. Well, for any matrix on here, any matrix on this line, sorry, any vector on this line, there's only one eigenvalue. It's a -1. No matter what vector you give me here that isn't the 0 vector, then after I do the transformation, it will be the same as just multiplying it by a -1. So it'll end up over here. Okay. All right, how about another eigenvector here? Yes? Anything that's on the line. Okay, so I could pick this. Yep, anything going there. I could have 1, 1. I could have a -1, 1. I could have pi, pi. I like that one. That sounds like a nice one, pi, pi. Okay. What's the eigenvalue associated with this eigenvector? 1. Just 1, because it doesn't change, right? It just stays the same after I reflect. It just stays there. So the eigenvector for that one, 1, 1, has 1 as the eigenvalue. Okay. All right, is this helping? Okay, yes, Phil? Yeah. So the question was, why did we say one of the eigenvectors is perpendicular to the line of reflection? If I pick another one, that's the only other line that it's the only line that gets mapped to itself with a reflection is the perpendicular one. I could pick another line here, like maybe this one. But after I get it reflected, I end up with something like that. So a vector here goes to here. They're not on the same line, right? But a line here, this line, after I reflect it, it stays on the same line. So that's the only one that works, other than this one, is the one that's perpendicular. So, good question. Okay, what's the other? Oh, scaling. We double the y component, we double the x component. So who has an idea on on an eigenvector here? What's one of the eigenvectors? Anyone come up with these? Yes. 1, 0. Claim 1, 0 is, so if this is 1, 0, why would you say that is an eigenvector? Nice. Okay, so if we do the transformation, which is the same as multiplying by a particular matrix, it's the same as just multiplying by a scalar. Okay, what's another one? Go ahead. 0, 1. And why? Okay. So this is like multiplying, this is doubling the length, this is tripling the length. Okay. I should do times 3. Okay. So, yeah, in this case, they're just the standard vectors. They're just the standard basis vectors. Those are the eigenvectors in this case. Okay. If you pick another one, I mean, what about the 1, 1 vector? Does it stay on that line if you do that transformation? It doesn't. 1, 1 goes to 3, 2. 3, 2 is like, well, if I do this correctly, it should be right there. But it goes to there. That's not on the same line. Well, it goes to, yeah, that. That's not on the same line. So, okay. And rotation doesn't have any real eigenvectors. No matter what vector you have that starts at the origin, it gets off the line that it spans. So you could do a 180-degree rotation, and that's okay. But, okay, we talked about that. So key about eigenvectors. So the eigenvectors are the basis of the null space of A minus lambda I. So this is when we were doing subspaces, I said that, hey, the null space is going to be the most important. That's going to be the one we work with. Yeah, this is why. Because eigenvectors are so important, and finding eigenvectors, you're finding a basis for a null space. So, and since A minus lambda I is non-invertible, we talked about that earlier, then the null space will have dimension at least 1. So sometimes the null space is just 0, 0, 0, but that's only if it's an invertible matrix. Like sometimes it's just the 0 vector. That's what I meant by 0, 0, 0. Okay, so any other questions? Yes?
What is the eigenvalue for 180-degree rotation?
Oh, so that question is, what's an eigenvalue for the 180-degree rotation? That'd be a -1. It'd be a lot like the reflection. So, because you'd end up same length pointing the opposite direction. So it would be a -1. So, good question.
I just
Yeah, you probably did.
90 degrees I, then I squared is -1.
Yeah.
Is that why?
Yes, that's a great way to think of it. So, okay. The rest of the slides are big picture things about the importance and application of eigenvalues. Let me just come out with this. Other than just the idea of matrix multiplication and understanding matrix multiplication, eigenvalues and eigenvectors are the most important thing to understand about a matrix, and it turns out that they're used everywhere, like all the time. Here's a simple example. So this is a population. This is a simple population model of rabbits and foxes. So the model is done by this simple matrix here. So the higher the number of foxes, they eat more rabbits. So then the rabbits will go down in population. And so I can change the population a bit. What does it mean? What if I start right there? What happens? This is the fox. The vertical axis is the number of foxes, and the horizontal axis is the number of rabbits. What's going to happen if their population starts right here where that red dot is? What's going to happen year after year? Yep. I did. In this situation, what's going to happen? Heather? The what? The foxes eat all the rabbits. The rabbit population goes to 0 after about 1, 2, 3, 4, 5 years. Okay? So what about over here? Here, both are happy. There just gets to be more foxes and more rabbits. What happens right? Oops. There's something right in here that's like crazy. What's going on there? I'm going to get this to a couple specific values. What does that mean? If they happen to start at that one spot, actually anywhere on that line, what does that mean? Right? Yeah, the ratio of the population stays the same. And in this case, they both continue to grow. So this turns out to be an eigenvalue, an eigenvector of that matrix right there. And that's a really important thing in the system, because if it chops the system up into two sides, and if you start on the left side of that, all the rabbits will die out. The foxes will win. But if you start at the right side, then everyone will be happy, I guess, if you like rabbits and foxes. But so these are they turn out to be important features in models to help you understand what's going on. Yes.
So if it's a system where it's not the eigenvalue, or it's either to the right or the left, is there like an asymptote for each given point?
So the question is there an asymptote to each given point? Not necessarily. There's not necessarily an asymptote for each given point in here, but it could be important in some models. Yeah. So good thinking. So just in the last couple minutes, I won't be able to do this justice, but I list off a bunch of applications. But one of them is principal components. It's a way to do data reduction. If you have these globs of data, then what you might care about is what direction is along those axes Like it looks like this axis right here, well, yeah, like those axes, look, those are really important, especially that really long one right there. Because it turns out that that might be the most important dimension that you care about. I did principal component analysis on our survey data. So remember, you took a survey on like your preferences early on, first week of class. So I did that. It doesn't quite make a blob like this because you guys are we have whole number values for things, but the principal components can find patterns in the data, and these turn out those vectors are eigenvectors. Those important directions are eigenvectors. These were the eigenvectors it came out with, and to interpret those, you get this. It turns out there's really only 3 dimensions, not 9. There's really only 3 dimensions, and it turns out that these are the 3 important dimensions. If you clicked high on you were a night owl, a last minute person, you liked summer, or you liked a friend group, you tended to mark high on those other ones. And if you marked high that you were a morning glory or early prepper or whatever, you liked winter, one-on-one, you tended to go high on something else. This dimension is maybe you might call the party dimension. I don't know. What should we? Well, pretty laid back dimension. How laid back you are? I don't know. Then you can see the other ones. There's ESPN sweats and hoodies and camping kind of went together. Netflix dress up and resorts went together. And video games and fixing a car went together, and board games and writing a poem and song went together. I didn't get gender in there. I think some of these might be affected by what gender you are, but I also did another analysis. And so if you were higher on the right side on that vector, you did better on the exam on midterm 1. Okay? Just saying. All right, have a great day. Did you